Okay, now chapter 6 AC. Okay, AC is an alternating current. Now, before that, let us do a quick recap of what we have learned from chapter 1 until right now. So chapter 1, we look at what is charge and how it works. What happens when you have two like charge and when you have two unlike charge. In chapter 2, we look at how charge flow in a capacitor in a DC circuit, okay, in a direct current circuit. And then in chapter 3, we look at what happens when the current is flowing through a resistor in DC circuit. And in chapter 5, we look at inductor. And again, it is for a DC circuit. Now, what is a DC circuit? If you look at this diagram, you look at the first statement, alternating current is defined as a current whose magnitude and direction change periodically. So what does it mean? So it means that, okay, maybe for the first half cycle, it's moving in the clockwise direction. And then after a half cycle, what happened? Now it changes its direction and it goes in the opposite direction, in the anti-clockwise direction. Whereas when it comes to a DC circuit, what is happening is that now, let's say this is your resistor, and then this is your power supply. So what happens right here is the current is just flowing in one direction, okay, without changing its direction. So it just keeps flowing in either clockwise or anti-clockwise direction. It is unlike your alternating current. It keeps changing the direction. Okay. So in chapter 2 and chapter 5, when we're looking at the capacitor and inductor, we learned that both capacitor and inductor, okay, both of them, they are storing energy. Okay, they are storing energy. And then in chapter 3, when we're looking at the resistor, the difference between the capacitor, inductor, and resistor is that resistor, it does not store energy, okay, whereas it uses up energy. So in this chapter, we're going to look at what happened when we connect these three components in a DC circuit. Okay, so first thing you have to know, of course, is the directions of current flow. And then the second thing that we're going to look at is the graph of the current flow through a capacitor, inductor, resistor, and also what happens when we combine them together. Okay, and then lastly, we're going to look at the power of each component. So AC current is a current whose magnitude and direction changes periodically, whereas when it comes to DC current, it's just moving in one direction. That is the first difference in terms of the circuit, in terms of the explanation. Now let's look at the direction. When you have an AC source is connected to a circuit, the alternating current that flow through the circuit and the potential difference passing through the resistor can be described by using IT and VT graph. Since the directions of the current, it keeps changing, so what happens in the graph is that it starts from 0 and then it slowly increases until it reaches the maximum value. I know this is the maximum value. Okay, this is the maximum value. And then it would start to decrease and goes back to 0. When it goes back to 0, what happens? Now the current will change its direction. So initially, they are flowing in the same direction, but with different magnitude. And then what happened? It will decrease. When it goes back to 0, then it will start to change its direction. Okay, and then it reached the negative maximum. Now this negative sign, the negative sign right here, it just means that now it's flowing in the opposite direction. Okay, opposite direction. The opposite direction increase and then decrease, go back to 0, and then it keeps repeating. So it will keeps giving you a sine function, a sinusoidal graph as shown in the diagram right here. Okay, and since we have V equals to IR, V will also have the same graph. Okay, V will also have the same graph. Why? Because we have V equals to IR and V is directly proportional to I, provided if you are looking at the same resistor. Therefore, when it comes to resistor, both of them, they will have the same shape, okay, the same type of graph. So how to describe this graph? Okay, so in order to describe this graph, you look at the shape of the graph. Now it is a sine function and it starts from 0. Therefore, okay, therefore I is equals to the amplitude, which is I naught. The graph is a sine, so sine omega t. okay, omega t. So that is the equation for I based on this graph. Now, can you have a cost function? Yes, of course. Oops. Of course you may. Okay, it's based on the shape of the graph. So if you are given, okay, if you are given a, oops, okay, if you are given a graph like this, then this will be a cost graph. Okay, this will be a cost graph. So it depends on the graph given. So for this given example, this is a sine function. Okay, and usually we will start from 0. Okay, we'll take a value that will start from 0 because we want to see what happens. We want to do a comparison between 3 different components. So I is equals to I naught sine omega t, whereas when it comes to V, okay, the equation for alternating current is V equals to V naught sine omega t. Now, these two equations, they are the equation for instantaneous value. What does it mean by instantaneous value? It is happening at a particular moment, okay, at a particular time. So meaning that if times is given, then you will have a difference I, okay? In other words, you can say when it comes to these two equations, your I and V, it varies with time, right? It changes with time. It depends on time. Different times you have a different value, okay? So these two equations, they are for instantaneous value. So you have to be extra careful with this. Why? So before we move on to the next part, let's see how many I and V we're going to have in this chapter. Okay, first thing, we will have I naught, which is the maximum value. We will have V naught, okay, which is the, okay, I'm going to start from I to make it easier. I naught, maximum value. We will have I RMS, which is the effective value. And then we will have I instantaneous, which is the instantaneous value. Okay, instantaneous value, effective value, which is the root mean square value, and then the peak value, I naught. Okay, and then we will have V. When it comes to V, it is slightly more complicated. Now, you just have the 3 of them. Why? Because it's flowing in a series. All components, they are being connected in series. But when it comes to V, okay, things will get slightly more complicated. Why? Because it depends on which component you are looking at. If you are looking at the source, of course, there's no issue. You're still going to have a V naught, V RMS, and a V instantaneous. Okay, V instantaneous. But then, remember the things that I told you before? In this chapter, we are going to look at these 3 components. And every single component, they will have their own V. Okay, they will have their own V. Meaning that other than the source, okay, this one is for the source. Other than for the source, you will have another set for capacitor. Okay, for capacitor. And then for inductor. And also for resistor. So when it comes to chapter 6, it is very important to write down the subscript. Otherwise, you're going to get confused. The V belongs to which component? The VRMS belongs to which components, and so on. Now, by default, if the question doesn't tell you whether that is a I naught, IRMS, or instantaneous, V naught, VRMS, or V instantaneous, by default setting, we assume it is RMS value because that is our effective value. Now, since you're a graph, if you look at the graph, okay, let us go back to the graph. If you look at the graph, the current, it keeps changing, okay? The value, it keeps changing with time. So we did an effective value. So the effective value, we determine it, we calculate it by using RMS, okay? We take RMS value as the effective value in the circuit. So when it comes to capacitor, what is going to happen? We will have V naught for capacitor. V, okay, now usually I will write the C first, okay? VC, peak value, VC, RMS value, VC, instantaneous value. That is for capacitor, okay? That is for capacitor. And then we have inductor, VL maximum, VL RMS, VL instantaneous. So that is for my inductor. And the last one, I have resistor, which is VR maximum, VR naught, VR RMS, VR instantaneous. Okay, VR instantaneous. So as you can see right here, how many V do I have? I have 12 V together in this chapter. Okay, saya ada 12 jenis V yang berlainan dalam chapter ini. That's why if you write it down without a subscript, if you record the value without a subscript, then you yourself are going to get confused throughout the calculation. You will get lost. You don't know which values to be used in your calculation. Okay, so all these component, okay, all this value, okay, they are used for different component in different situation. Make sure you don't choose the wrong value. Once you're able to distinguish which one belongs to capacitor, inductor, and resistor, and it's either the V peak, V RMS, or V instantaneous, this chapter actually is very simple. Okay. So the most important thing is to know how many type of V that you have in this chapter. Okay, and also record the value together with a subscript. Without subscript, you yourself are going to get lost in your calculations. All right. So now let us go back to here. Okay, so these two equations, when it comes to the equations with the sine function, sine omega t, this is the instantaneous value. Why? Because it tells you it varies with time. It changes with time. Okay, so I equals to I naught sine omega t, V equals to V naught sine omega t, and this is for a resistor. Okay, because right here, these two graphs, it gives you, okay, according to the situations given, now this current is passing through, the AC current is passing through resistor. So these two graphs, they belong to resistor. Now, of course, when we go through this chapter, we are going to learn various type of graph. Okay, we got the graph for capacitor, we have the graph for inductor, and you have to know all those graphs. Okay, semua graph Anda kena tahu. Kalau Anda tak tahu graph, maka Anda tak boleh jawab nanti. Because the graph is very important. Okay, you needed to sketch a Phasor diagram in chapter 6. What does it mean by Phasor diagram? Well, we'll look at it in a bit. Now, let us go through a few terms first. Okay, important terms in AC. In chapter 6, okay, in chapter 6, we're going to see these few terms very often. It's the frequency. Now, what does it mean by frequency? It is defined as the numbers of complete cycle in 1 second. Therefore, the unit is per second. Period is the time taken to complete 1 cycle. Okay, the unit is second. So period is very important. Remember why? Because if you need to sketch the graph, okay, if the question asks you to sketch the graph, then you're going to need period to calculate what? To calculate omega. Okay, so omega equals to 2 pi f, or omega at the same time is equals to 2 pi over t. Okay, so all these terms, they are very important in chapter 6. Because questions will ask you to play with all these terms and also the equations above. So the peak current is defined as the magnitude of maximum current that you can have in 1 cycle. Okay, the magnitude of the maximum current. Therefore, when it comes to the graph, okay, here the peak value, the highest point is our peak value. Okay, this dotted line, it touches our peak value. Now, sometimes questions will ask you to calculate from peak to peak value. What does it mean by peak to peak value? Peak to peak value means it's going from maximum peak value until the negative peak value. So after you calculate peak value, you have to times 2. Okay, so it is actually V naught plus V naught from peak to peak value. Okay, this is what we call peak to peak value. So peak to peak value means it's going from the positive maximum to negative maximum. What is the value between these 2 points? That is the meaning. Okay, that is the meaning. So you just times the peak value with 2. All right. So peak value is the maximum magnitude, the magnitude of maximum, either the maximum current or maximum voltage. So what does it mean by root mean square value? Okay, just now I told you it's the effective value. Now let us go through the definition. Okay, let us go through the definition. So root mean square current is defined as a stable value. okay, a stable value or an effective value of an alternating current when flowing through a resistor, while the dissipated average power in the resistor is equal to the dissipated power when a direct current flowing through the same resistor. Okay, so you calculate dissipated average power. This power is same as the dissipated power when you use direct current. So it is a stable value, it is an effective value. Okay, so dissipated average power in resistor is equal to the dissipated power when a direct current flowing through the same resistor. So it doesn't matter whether you're using AC or DC, it's going to have the same value. So the formula for IRMS is IRMS is equals to I naught over square root 2. Okay, I naught over square root 2. Whereas root mean square voltage is defined as the values of a steady direct voltage when applied across a resistor produce the same power. Once again, you're looking at the equality in terms of power. Okay, so it produces the same power as the average power produced by alternating current across the same resistor. Okay, so DC and AC, they give you the same power. So that is the values that we record as the RMS value. So VRMS is equals to V naught over sub 2. Okay, V naught over sub 2. So that is the root mean square value. Yeah. So and at the same time, 1 over sub 2 is equals to 0.707. So when it comes to the graph, okay, sometimes you will see the questions, they might give you here, the value, okay, this value, and it tells you this is 0.707 V naught, which actually represent your root mean square value. Okay, your RMS value. So RMS value at the same time is equal to 0.707 I naught or 0.707 V naught. So sometimes graph will give you, okay, so this one, it actually represents your RMS value. So it is somewhere slightly lower than your maximum value, okay. So that's it. Okay, so root mean square value in your syllabus, what you have to know is the definition. We focus on the definitions and also how to use these two equations. Okay, kita tak tengok secara mendalam untuk IRMS and VRMS. Our main focus is how to apply these two equations in an AC current, okay, to calculate all the other value. So remember, in chapter 6, if the question just tells you now you are given a current that is equal to 2 ampere, then that current is actually representing root mean square value, okay, the stable value, the effective value in our circuit. Unless the question states that, okay, the peak current given is 2 ampere, then the 2 ampere belongs to I naught, okay, your peak value. All right. So now let us go through the resistance, reactance, and impedance. So reactance and impedance, they are the new terms. Okay, they are new to you, but we will look at them later on. Right now, let us go through the most important things in chapter 6. If you know how to sketch Phasor diagram, then you should be able to answer all questions in chapter 6. Because all questions, okay, it doesn't matter the question are you to sketch diagram or not. All questions, they are mainly based on the Phasor diagram. Okay, so 6.3a, sketch and use Phasor diagram and a sinusoidal waveform to show the phase relationship between current and voltage for a single component circuit consisting of pure resistor, pure capacitor, and pure inductor. Now, what does it mean by pure? Pure means it is an in ideal situation, ideal condition. Okay, no energy loss. It is not being affected by any external factor. So that is the meaning of pure, okay, in a perfect condition. So what the questions want, what the learning outcome wants you to do is ask you to explain the relationship between current and voltage by using two methods. The first method is based on the Phasor diagram. Okay, the first method, you explain the relationship by using Phasor diagram. And the second method, you explain it by using sinusoidal waveform. Okay, you plot a graph to explain the relationship. So how to plot a graph? Exactly like the one that I showed you just now. Okay, the sine function, the sine graph. So we are going to learn both in this 6.3. Okay, so your Phasor diagram and also the wavefront. Two method can be used to explain, okay, explain the relationship between I and V. So what types of relationships that we want to explain? Okay, we want to explain it in terms of whether they are in phase, okay, or they are out of phase. Okay, or they are out of phase. If they are in phase, then that is fine. If they are out of phase, then you have to explain whether which one is lags behind, okay, and then which one is leading in the relationship. What does it mean by lags behind and leading? Don't worry, I'll explain it to you in a while. All right. So now let us go through what does it mean by Phasor diagram first. What is Phasor diagram? Phasor itself is a vector. Phasor is actually a vector, but it is not a static vector. It is a vector that always rotates, and it rotates in the anti-clockwise directions about its axis with a constant angular velocity. Okay, so it is a vector, for example, okay, this is the vector, but this is not a static vector. Okay, it does not just point in a one direction. This vector is rotating. Okay, it's rotating in the anti-clockwise direction. So when you sketch it, you need to show this arrow and with the omega in the diagram to show that this vector it's rotating. For example, if you sketch a Phasor diagram for I, so I, it rotates in the anti-clockwise direction. Why anti-clockwise direction? Well, because we use a sine graph, we project it to a circle. Okay, if you project it to the circle, then what is going to happen? Now let's look at the graph here. Okay, let's focus on the red color line. We're going to see what happens to the current. So if you look at this diagram, the diagram on the left-hand side, the current starts from 0. Okay, the current starts from 0. So the I, it's also start from 0. Okay, so the 0 is actually starting from here. Okay, the horizontal line. This line, it represents 0 degree. Okay, so your I start from here, the 0 degree. And then why we say it rotates in the anti-clockwise direction? Because let's look at the graph on the here, okay, the sine graph. When the angle increase, when the value increase, the angles also increase. Okay, the angles also increase. So it can only happen if this vector is rotated in the anti-clockwise direction. If it rotates in the clockwise direction, then it means it's flowing in the negative direction. Okay. So Phasor is a vector that rotates in the anti-clockwise direction. Why? Because we use the projections on the from the sine graph. We project it to get a circle. So this sine graph, as the value increase, when it reaches the maximum value, you can see that now it's 90 degree. Okay, it gives you a straight line. Okay, so it gives you a straight line here. So projection, kamu project. Daripada graph, kamu project a circle. Okay, and by looking at this graph, you should know that what is the angle. Okay, after you project it, what's the angle between your I and V. And then as it keeps moving on, okay, now if it keeps flowing, let's say now it keeps flowing, it decreases. Okay, because this is a AC current. AC, now it decreases. After it reaches the maximum value, it decreases. So what happens in the circle? Now it keeps rotate. Okay, it keeps rotate. And now it reaches a 0 value. And this position, it represents 180 degree, half cycle. Okay, based on the sine graph, now the current is flowing in a half cycle already. Okay, the current already passes through the half cycle. So it goes back to 180 degree, okay, or 0 degree. Okay, so what happens after this is keep flowing. Okay, it keeps flowing. So it flows, now it reaches the maximum, okay, the negative maximum, the maximum negative value. So now your circle, it keeps rotating. Okay, it starts from 0 and then it moves towards negative maximum. And when it reaches I naught, negative maximum I naught, it gives you another 90 degree from your original value, from your zero. Okay, it gives you another 90 degree right here. So if you look at the graph again, it's a projection. Okay, so kamu buat satu garis lurus, actually dia project. Setiap titik daripada kita punya graph is projected onto the circle. Okay, so as it keeps going on, it keeps moving, it goes back to zero. And then the cycle is start again. So it keeps moving in the anti-clockwise direction as your current is flowing. Okay, as the current is flowing in the AC circuit, it keeps moving in a circle. So it will just move until the end, until you stop the current. So same things, okay, same things go for V, okay, because remember, when it comes to resistor, okay, when it comes to resistor, V is equals to IR. So what happens in I is actually representing what happens in V, because their relationship is directly proportional. So bila kita ada relationship directly proportional, apa yang berlaku untuk variable pertama adalah apa yang berlaku untuk variable kedua juga. Okay, same things. That's why if you say I increase, what happens to V? V also increase. If I increase by 3 times, what happens to V? V will also increase by 3 times. Okay, so bila kamu ada soalan yang increase berapa times punya, actually you can refer to the relationship. Okay, so if I increase by 3 times, V also increase by 3 times. So the graph, okay, since the graph I start from 0, your V also start from 0. This one is for resistor. Okay, this one is for resistor. Only for resistor, not for capacitor and not for inductor. Why? We'll find out soon. Now let us go back to phasor again. So phasor is a vector. Phasor diagram means it is a diagram containing phasor. So we call it phasor diagram. Of course, in a phasor diagram, you will have 2 or more phasor. Okay, 2 or more phasor. So it is used to represent a sinusoidally varying quantity, such as AC current and your alternating current, which is AC, or alternating voltage, AV. Okay, ada buku dia terus tulis a short form. Okay, AC and AV. But usually we use AC current. Okay, AC for the current. So it is also being used to determine the phase difference between current and voltage in AC circuit. Okay, so we use it to determine phase difference. So what does it mean by phase difference? Remember, phase representing angle in our equation. Okay, phase is the angle in our equation. We have a, okay, let's go back to the equation just now. Just now we have equation V equals to V naught sine omega t, and then I equals to I naught sine omega t. Okay, so this part representing phase. So we want to see what is the phase difference between these two equations, between current and voltage. Okay, by looking at phasor diagram. Because once you have phasor diagram, it should be easier for you to tell what is the angle between these two variables. Okay, this V and I. So if they are the same, for example, right here, omega t and omega t, then we say the phase difference is 0 and thus they are in phase. Okay, so from the figure above, we have I equals to I sine omega t, V equals to V sine omega t. So the phase difference between them, you use omega t minus omega t, and therefore you get a 0. So either you determining it from the sinusoidal wavefront, okay, from the sine wave, you form an equation for them, okay, and then once you obtain the equations, you can calculate the phase difference by using this method, or you can look at the components given and then you sketch the phasor diagram straight away. And from the phasor diagram itself, you yourself should be able to tell which one is leading, which one lags behind. Okay, so leading, for example, if, okay, now for example, okay, this is just an example. If your V, kalau lah V anda, if you have a V which is V naught sine omega t plus pi over 2, and you have a case where I is just equals to I naught sine omega t, what happens right here? How to calculate the phase difference? So you use this part minus this part. Okay, kalau kamu guna this one minus this one, so we have omega t plus pi over 2. okay, which is the phase for voltage minus the phase for current minus omega t, it gives you pi over 2. When you have a case with a positive value, you use V minus I, you obtain a positive value, then this one, it represents your voltage leads I by pi over 2 radian, okay, by pi over 2 radian. But if, can you get a negative value? Yes, you can. If you use I minus T, okay, if you use I minus V, so phi I minus phi V, it will give you what? Phi I, you have a omega T minus this one, omega T plus pi over 2. Then, of course, this one, it give you negative pi over 2 radian. So if you have a negative sign right here, then what does it mean? It simply means now your I, because you use I minus V, so you need to mention I first. I with a negative sign means it lags behind. V by pi over 2 radian. Okay, so in your explanation, the I and V, you just follow the sequence in your explanation. Okay, if you use I minus V, then you say I is lags behind V. If you use V minus I, then V leads I. Sequence dia sama. Okay, dalam kamu punya equation and your explanation, V and I, they are located in the same position. Just that you have to determine whether it's lags behind or it leads. Which one? How to tell whether it's the lags behind or the leads? You look at the final answer, whereas it is negative value or positive value. Okay, so you yourself have to know how to describe all this term because you need to mention it in your final answer. Okay, kalau soalan minta Anda kira phase different, selepas Anda kira, Anda kena sebut which one leading, which one lags behind. And then how do you know? That is how you do it. Okay, that is how you do it. Now, sometimes, of course, you can tell from the Phasor diagram. But sometimes, if question give you these two equation or these two equation, then you must calculate it based on the equations given. Okay, you must calculate based on the equations given. So now I give you some time to write out this example because I believe it will give you a better idea on how to calculate phase difference and so on. Okay, so saya bagi Anda beberapa menit untuk catat contoh ini dalam buku Anda. Okay, supaya Anda tahu apa maksud lags behind, apa maksud leading, macam mana nak kira dan sebagainya. Okay, so I hope you right now you understand what does it mean by lags behind, what is a leading, and then what is a phasor diagram. Okay, so phasor diagram, you need to understand the idea, the concept, how to obtain the diagram right here. It is actually the projections of our sinusoidal waveform. Okay, daripada kita punya wave, kita project dia menjadi circle. The idea is very similar to the things that you have learned in circular motion in SEM 1. Okay, kalau kamu dah lupa macam mana dapat projection, well, perhaps you can go through the notes again. Okay, so before we proceed to a pure resistor, pure capacitor, and pure inductor, now let us go through important terms. Okay, we need to understand a very important terms in the chapter 6 first. So chapter 1, 2, 3 is a direct circuit. Okay, direct circuit with just one component. When you have more than one component, then how are you going to calculate the total oppositions of a current in a circuit? Now we use the term impedance. Impedance is a new term. Okay, it's a new term. It measures the oppositions of a circuit to the AC flow. Okay, what is the things that resist the flows of current in a circuit? Okay, so the scalar, it is a scalar quantity and the units is ohm. So how to calculate it? So basically Z is equals to VRMS over IRMS, which is also equals to V naught over I naught. It must be coming from same family. Okay, so basically the idea is same as the resistance in a DC circuit. Okay, so in a DC circuit, impedance is just like a total resistance. But now in AC circuit, Z is not equals to R. Why? Because when it comes to this chapter, we are looking at three components. Okay, so Z is actually contain R, C, and L. It look at the oppositions of current from these three components, not just from one component. And of course, in a DC circuit, Z is just equals to R. But in an AC circuit, that is not the case. Okay, kamu kena tengok the oppositions coming from all three components. So basically, Z, it contains these three things. Okay, but since it's measuring the oppositions of the current in a circuit, so the unit is in terms of ohm. Okay, you calculate it by using ohm. So VRMS is equals to IRMS Z. Now, of course, this is coming from the source. Okay, this is coming from the source. You cannot use VCRMS to calculate Z. You cannot use VRRMS to calculate Z if you have more than one component. If you have just one component, yes, of course you may. Okay, because if you have just one component, then V source is equals to VR. V source is equals to VC. V source is equals to VL. But if you have more than one component, then you cannot use VRRMS, VCRMS, or VLRMS to calculate Z. Okay, it must be coming from the source or it must be the total V in the circuit. Okay, total VRMS. If you're going to use V naught, then the partner must be I naught Z. If you use V instantaneous, then it should be I instantaneous Z. Okay, must be coming from the same family. Dia tak boleh silang. You cannot use V RMS and I naught to calculate Z. Cannot. So how to change between these two equations, especially the first two? Sometimes questions might give you V RMS and I naught. So what are you going to do? Then you have to use the equation in a previous subtopic. IRMS equals to I naught over square root 2. VRMS equals to V naught over square root 2. Okay, you use these two relationships to change it, okay, to play with the value until you obtain the value from the same family. Soalan di chapter 6, kenapa pelajar pening? Sebab dia agak suka bagi kamu maklumat bersilang. Apa maksud maklumat bersilang? Dia bagi kamu RMS di sini, dia bagi kamu I naught. Tetapi dia suruh Anda kira Z. How you calculate Z? You need to add an additional step. So you can transform all informations into same family by using these two equations. Okay, so actually dua equations ini dia memainkan peranan yang sangat penting di chapter 6. Okay, sebab kalau soalan bagi kamu nilai daripada keluarga berlainan, Anda guna dua equations ini untuk tukarkan dia menjadi keluarga yang sama. Okay, you change it into the same family. So that is the Z. Okay, that is Z. Now, why can't we call all three, okay, all the opposition from a three component as a resistance? Because this one need to go back to the first slide. Because like I told you just now, okay, resistor, it use energy. But then capacitor and inductor, they just store energy. So you cannot call them resistant. So in this chapter, rather than calling it as a resistant, when it comes to C and L, we just call it reactance. Okay, R we uses resistance, but when it comes to resistance, when it comes to capacitor and inductor, we call it reactance. Why we call it reactance? Because what happens in a capacitor and an inductor, if you remember, they just store energy. Okay, first half cycle they store energy, second cycle they release energy. So they just react to the circuit. Okay, dia cuma react, whether it's receiving, returning, receiving, returning. They are not using up any energy. So that's why we cannot call it resistant. When it comes to resistant, it uses up energy. Okay, it uses energy. So that is the main difference between resistor and capacitor inductor. Okay, capacitor and inductor, they are very similar. Remember the main difference between them? The main difference between them is capacitor store energy in electric field, and then inductor store energy in magnetic field. But both of them, they are storing energy. So after store, what happened? They will release the energy if it needed to. Okay, if the system needed to release the energy, then it will start to release energy. So it's actually receiving and then releasing. Receive, return, receive, return. That is what happened in C and L in our AC circuit. So that's why when it comes to chapter 6, we give it another new name called impedance to calculate the summations of resistance and reactance in order to add them up. Because they're actually a form of oppositions of a circuit to the AC flow. Both of them, they oppose the flow of current. Okay, when they react. It doesn't matter when they react or when they use energy, but they are the oppositions of a circuit to the AC flow. Okay, so the only difference is their function. That's why we give them different name. But if you want to calculate the summations of resistance and reactance, then we call them impedance. Impedance is the total of resistance plus reactance. Okay, so I hope you don't get confused, yeah? Because in this chapter, you are going to have a lot of terms. The first terms that you have is the resistance. Okay, resistance, which is R. And then you have inductance. Inductance, of course, you have two different inductance. The first one is capacitive reactance. Okay, capacitive reactance, which is your XC. Okay, and then you have inductive reactance. Okay, semua terms, but this is XL. And then you have capacitance. Okay, capacitance, which is your C. And then inductance, which is L. Okay, so don't get confused between these 5 terms. All right, because they all carry different meanings. They all play different roles in the calculation. Okay, they all play different role in the calculations. And when you combine the first 3 together, it is known as impedance, which is your Z. Okay, which is your Z. So I give you sometimes to write it down. Okay, saya bagi anda beberapa minit to write it down. Why? Because all these terms, they are very important. Kalau kamu tak boleh beza terms ini, maka anda tak boleh buat pengiraan. Okay, this chapter is very simple. Why? Because usually you will have a short question. What does it mean by short questions? Okay, maybe the question just asks you to, okay, now calculate capacitive reactance, or calculate capacitance. That type of questions will be given in the exam. Okay, so usually you just need to apply one equation, then you can solve it. But the issue is whether you understand what does it mean by capacitive reactance or not. What is the difference between capacitive reactance and capacitance? That is the part where students always got confused. Pelajar kenapa dia tak boleh jawab chapter ini? Sebab dia tak boleh beza term-term yang saya tulis di sini. Soalan minta kira impedance, dia pergi kira capacitance. Soalan minta dia kira inductive reactance, dia pergi kira inductance. Habis. Why? Because you don't understand the meanings of the terms. Okay, so you need to be able to tell what does it mean by capacitive reactance, inductive reactance, capacitance, inductance, and reactance, and so on. Okay, if questions ask you to calculate impedance, what is the values that you need to use in your calculation? You need to use R, XC, and XL. Okay, R, XC, and XL. Okay, especially when it comes to XCC, XLL, pelajar sentiasa keliru. Okay, dua ini dia tak sama. Dua ini pun dia tak sama. Okay, dia tak sama. So make sure you are clear. Okay, now let us go through the component one by one. Okay, kalau kita dah boleh faham component one by one, then the rest should be very simple, very easy. So figure shows an AC source connected to a pure resistor. So this is the diagram. Okay, when it comes to this set of derivation, you need to know how to sketch the diagram. You need to know how to sketch the waveform, and then you need to know how to sketch the phasor diagram. Okay, because all this can be asked in questions. Soalan memang dia boleh minta Anda sketch semua benda ini. So sketching yang Anda di muka surat ini semua Anda kena tahu. Okay, all this sketching you have to know. So figure shows an AC source connected to a pure resistor. So you have a pure resistor right here, which you see now they label it as VR. So the V without subscript is for the source. In a question, if you are given the value, then the value representing RMS value. Unless it's stated there, that is a peak value, then that one you have to treat as peak value. Okay, so you see, subscript is a must, so that you yourself don't get confused. And the equations that we derive right here, actually they are all for VR. Okay, our derivations, our calculations, most of them, they are focusing on the component. So if the alternating current passing through the resistor, okay, the current can flow through without any issues. So we have I equals to I naught sine omega t. The moment you switch on the power supply, it starts from 0, then it starts flowing through the resistor. So since V equals to IR, okay, substituting the equations into the here, therefore you will obtain VR equals to VR equals to VR naught. Okay, VR naught sine omega t. Okay, VR equals to VR naught sine omega t. So that is the things that you have to take notes. All right. So this equation, the equations for V is actually for what happened across resistor, not the whole circuit. Okay, not the whole circuit, but just what happens across the resistor. So VR equals to VR naught sine sine omega t. Sorry. Okay, sine omega t. So the AC voltage across the resistor at any instant is, okay, so that is what you obtain. Okay. So what happens right here, okay, we just sketch the graph based on these two equations, okay, combining these two equations, we obtain a waveform here, and then from here, we transform it into a phasor diagram. So from the phasor diagram, okay, actually you can straight away tell from the phasor diagram, or you can do it based on the calculation as well. The phase difference between V and I is del V equals del phi equals to omega t minus omega t equals to 0. Okay, equals to 0. Or straight away, you can actually say the phase difference between them is 0 because you have the phasor diagram already. Okay, kalau Anda ada phasor diagram, tak semestinya kena tunjuk ini because you can tell what is the angles between two of them. Now, since two of them, they are parallel and overlapping with each other, so the angles between them is definitely 0. One more thing I forgot to mention. When it comes to phasor diagram, you don't need to show the circle. Circle here in this diagram, it just tells you it keeps rotating according to the wavefront given. When it comes to problem solving, bila dia datang ke soalan, how are you going to sketch the phasor diagram? You just sketch like this. This is your I, this is your V. This is the origin, and then they rotate in the anti-clockwise direction. Remember, circle is not part of the phasor diagram. Okay, circle is not part of the phasor diagram. They're just showing you here in this diagram in your notes because of the waveform. Okay, because of the waveform. Waveform, it keeps rotating. So when it's projected onto the diagram, you obtain a circle like this. But when it comes to questions, when you want to sketch a phasor diagram in your questions, this is what you should do. Okay, so remember, circle is not part of the Phasor diagram. Okay, the circle in the diagram here is just show you the path. So when you sketch it, that is what you should do. Okay, the purple color diagram on the right hand side, that is what you should do. So I and V, they rotate in the anti-clockwise direction. So looking at the diagram itself, straight away you can tell the phase difference is 0, and thus in a pure resistor, that is how you should answer the question. The current and the voltage, they are in phase. The key words right here is in phase. How do I know in phase? Because phase difference is 0. Okay. So if you have a pure resistor circuit, meaning that you have just one component, the impedance Z is equals to VRMS over IRMS equals to V0 over I0 equals to R. Okay, and this VRMS and V0, they are actually VRRMS and VR0. Okay, but it doesn't matter. Right here, they just write VRMS and V0 because you just have one component. Okay, when you have just one component, VRRMS is equals to VRMS. Kalau ada satu component sahaja. Okay, kalau ada satu component sahaja. So in this pure resistor circuit, Z at the same time it is equals to R because you have just one component. Okay, this is only true because you have one component. In the circuit. Okay, if you have more than one component, then Z is no longer equal to R. Okay, so keep that in your mind. Z sama dengan R di equations di sini sebab kamu cuba ada satu component sahaja in a pure resistor circuit. If it's not pure resistor, then no. Okay, this is no longer valid. This is no longer correct. Right? So that is the first component, the first things that we learned in chapter 6, pure resistor. We're going to look at 6 different cases in this chapter. Okay, kita akan tengok 6 case di chapter ini. Case pertama adalah pure resistor. So pure resistor, we are done. We have already learned how to sketch the diagram. That is the first thing that you need to know. And then what is the I and V in terms of a sine function? This is the second thing that you have to know. The third thing you have to know is how to sketch the waveform. And then how to sketch the phasor diagram. From here, we then determines the phase difference between the two, between your V and I. So for every single component, you need to know these 5 things, at least these 5 things. Okay, and of course, all the other additional things, for example, such as Z and so on, okay, we will learn how to calculate it afterward. But the fundamental thing are the 5 things right here. Okay, adalah 5 benda di sini. So, 5 benda untuk setiap pure component you have to know. Alright, now let us proceed to the second one, pure capacitor. Pure capacitor, it means there's no resistance or inductance effect in the circuit. Okay, so this is a pure capacitor. So what happens in pure capacitor? Well, initially we know that VC is equal to 0. Okay, and it increases as the time goes by. So if you have alternating voltage across the VC at any instant, okay, then the value can be calculated by using VC equals to VC peak value sine omega t. Okay, VC peak value sine omega t. So from this equation, we then want to derive what is the relationship between V across capacitor and also current. Ini yang kita sendiri derive. So at the beginning, we don't know what is the relationship between V and I. Okay, well, we might know when I increase, V decrease. Okay, because we have learned what happens in capacitor. But we don't know what is the exact difference between the two of them. Yang kita belajar di chapter 2, kita cuma tahu apabila kita punya VC bertambah, kita punya current kurang. Sebab apa? Sebab electron slows down. That is what we learned in chapter 2. but we don't know the exact relationship. We don't know how fast it is. We don't know what is the speed, what is the difference between the two, what is the phase difference between the two. So what are we going to do right now? We want to derive the equation. Okay, equation can tell us the exact relationship between I and V. So the equations of alternating current in the capacitor is I is equals to dq over dt. Okay, so Q according to equations, CV equals to Q over V. We arrange it, you obtain I equals to dCV over dt. So VC right here, okay, oh, not CV, it's a VC. Okay, C equals to Q over VC. So VC right here, okay, why we want to substitute this one into the equation? Because we want to make sure our equation come with a VC. Kalau tak ada VC, kita tak boleh derive. So I equals to dc VC over dt. Therefore, we can plug this equation into here. Okay, so what happens after you substitute into the equation? Well, you now try to rearrange the equations. So you can take C and V out, okay? Because C and V right here, they are constant value. Okay, your C and your maximum value, they are constant, so you can take it out. So now you have I equals to CV naught d over dt sine omega t. So if you integrate this equation, differentiate this equation, you will obtain I equals to CV naught omega cos omega t. Okay, and we know that this part is actually representing I naught. Okay, it's representing I naught. Therefore, we can write it as I equals to I naught cos omega t. Okay, I equals to I naught cos omega t. Okay, so by looking at these two equations, straight away you know that they are not in phase. Why? Because now your VC is in terms of sine, but your I is in terms of cos. Okay, your I is a cos omega t. But cos omega t and sine, how are we going to calculate the phase difference? It's a bit hard, right? So you need to think, how are you going to transform cos into sine? Well, I at the same time is equals to I naught sine omega t plus pi over 2. Okay, plus pi over 2. So once you transform into a sine function, you can then calculate the phase difference between VC and I. Okay, VC and I. So remember, cos omega t is equals to sine omega t plus pi over 2. Okay, so from the derivations, you obtain I equals to I naught cos omega t. So you transform into the sine form so that you can calculate phase difference. If you want to calculate phase difference, you must make sure both of them they are in the same trigo function. Okay, kamu tak boleh guna cos tolak sine, tak boleh guna sine tolak cos. Okay, cuma sine punya boleh tolak sine punya, or you change the sine into cos. Then yes, you can use cos minus cos. All right. So I naught is equals to CV naught omega. Okay, I naught is equals to CV naught omega. This one, okay, this one, it has a function. Okay, we will keep it for later. Right now, just leave it first. Kenapa ini penting? Okay, we will use it in the next page. Now let us go back to the graph first. Okay, biar kita kembali kepada graph. So how are we going to sketch the graph? Initially, you have V. Your V is a sine function. Okay, your V is a sine function. So sine is start from 0. Okay, so your V is start from 0. So from 0, then it start to move in a sine function. Okay, sine form. Whereas for your I, okay, your I equation is a cos omega t. Cos omega t means it's going to start from the maximum value. Okay, so from maximum, then it move in a sine wave. Okay, in a sine wave. If you project it onto a Phasor diagram, V start from 0, okay, V start from 0. Therefore, your V, your vector V is lying on the x component. This one, it shows that your V start from 0. Your V is a sine function. Okay, and then your I, because it's a cos function, it starts from a maximum value. Therefore, now the Phasor diagram start from 90 degrees. Okay, but both of them, remember, when you sketch the phasor diagram, you need to show the directions of rotation. Both of them, they are going to rotate in the same directions at the same rate. Okay, at the same rate. So you have a V and I as shown in the diagram right here. So from the diagram itself, straight away you know the phase difference is pi over 2 radian. Now you see, that's why I told you, if you know how to sketch phasor diagram, you can actually get quite a lot of information from the phasor diagram. All right. So the first and the most fundamental things that you can get from the phasor diagram is the phase difference between V and I. So according to the phasor diagram right here, you have I and V. The phase difference is pi radian, pi over 2 radian. Which one leading? That is the question. If you look at the diagram, since both of them, they are rotating in the anti-clockwise direction, therefore, according to this diagram, I is in front of V. Because both of them, they will rotate towards the anti-clockwise direction. So I is in front. Based on the phasor diagram, I know that my I leads V, okay, by pi over 2 radian. But what if I want to show it by calculation? Then, of course, again, we can use delta phi. Okay, delta phi. So it's up to you whether you want to use I minus V or V minus I. Okay, so for example, because now I already know I leads V, right? So I'm going to use phi I minus phi V. So phi I have, okay, remember what I told you just now. If you're going to use sine, then both of them, they must be sine. Okay, jangan guna yang cos punya. So don't use omega t minus omega t. What you should use in the calculation for I is omega t plus phi over 2. Okay, minus omega t. So which is pi over 2 radian. It is a positive value. Okay, it is a positive value. Therefore, I know that my current leads VC by pi over 2 radian. Okay, or if you use phi B minus phi I, then you will find that VC lags behind I by pi over 2 radian. In exam, it doesn't matter which ones you write. Both of them, they are correct. Okay, both are correct. So that is the phasor diagram and the phase difference for pure capacitor circuit. Okay, so in a pure capacitor, I always leads V by pi over 2 radian. Okay, I always leads V by pi over 2 radian. Then how are we going to calculate impedance? So from the definitions of impedance, we have Z equals to V naught over I naught. Remember the I naught that we derived just now? In our derivation just now, we found that I naught is equals to CV naught omega. So you plug it into the equation, V naught and V naught cancel out. Z is actually equals to 1 over omega C, okay, which is also equals to XC. So that is the relationship between XC and C. Okay, that is the relationship between XC and C. So in a pure capacitor circuit, you can calculate the impedance by using V naught over I naught and of course VRMS over IRMS. Okay, but at the same time, it is also equals to XC. Okay, where XC, because omega is equals to 2 pi F, XC can be written as 1 over 2 pi FC as well. Okay, 1 over 2 pi FC as well. So meaning that how many methods can be used to calculate XC and Z? Okay, so when it comes to pure capacitor, Z can be calculated by V naught over I naught. It can be calculated by VRMS over IRMS. It can be calculated by using 1 over omega C or 1 over 2 pi FC or straight away equals to XC. All right, so all these, okay, all these, they can be used to calculate impedance or capacitive reactance. Okay, so XC, the name is known as capacitive reactance. What is the relationship between XC and C? That is the relationship between them. Okay, that is the relationship between them. So XC and C punya hubungan ditunjuk dalam equations di sini. All right, so you yourself have to know what is the difference between XC and C and how to calculate capacitance or capacitive reactance. Okay, because this is a most common since mistake in chapter 6, where students you got confused between XC and C. Memang sangat biasa, walaupun dah banyak kali tekan, tapi pelajar masih keliru antara XC dengan C. Alright? So the capacitance reactance is the oppositions of a capacitor to the alternating current flows and is defined by, so that's what I showed you just now. So XC, it is equals to VRMS over IRMS equals to V naught over I naught. Okay, now this one you can use it from the source as well, because now you have just one component in the circuit. If you have more than one component, then XC must be calculated by using VC RMS over IRMS, VC naught over I naught, if you have more than one component. But if you have just one component, for example, this one, a pure capacitor circuit, then this is the equation that can be used. All right. So capacitive reactance is a scalar quantity and its unit is ohm. Okay, its unit is ohm. So the relationship between capacitive reactance and the frequency can be shown using the graph below. Okay, according to the equations, XC equals to 1 over 2 pi FC. The relationship between XC is inversely proportional. Inversely proportional graph, it gives you this graph. Okay, that is the graph for inversely proportional. Right. Then how about a resistor? Just now for resistor, we don't have the graph, right? Because resistor, it doesn't depend on the frequency. Okay, resistance, it does not depend on the frequency. Meaning that if you want to sketch a graph of, for example, R, where's my pen? Okay, here. R against F, well, since it does not depend on the frequency, therefore you will just have a straight line. Okay, untuk resistor, that is what you're going to get, just a straight line. Because of what? Because it does not. Okay, because R does not depend on F. So the one that depends on F is your XC. Okay, if it's your XC. So that is the graph for R. Okay, so for XC, sudah diberi di sini. So XC against F, that is the graph that you get. Okay, because of here, inversely proportional. Pure inductor. Okay, pure inductor. So what happens in a pure inductor? Pure inductor means that there's no resistance or capacitance across the inductor. Okay, or these two effect in the AC circuit. What you have is just VL and V. So here we're going to start from current. Okay, why? Because initially you don't know what is the value of VL. You just know that there is a back EMF across inductor, but you don't know the value, and you don't know what is the relationship of VC and VL, sorry, not VC, VL and I. Okay, you don't know the relationship. What you do know is there is a back EMF, but you don't know the value. You don't have any other information about it. But what you do know is it should start from 0 in this case. The moment you switch on the power supply, the current will start to flow through it. Okay, but of course it's not in a constant value. Why? Because you have a back EMF right here. It will slow down the current flow across the VL. The current is flowing through inductor slowly. Okay, at an increasing rate. Okay, that's why you have EMF equals to negative inductance L, negative L di over dt. It is not in a direct rate, it is not in a constant rate, but it builds up slowly. Okay, it builds up slowly. But what we do know is start from 0. So for alternate current passes through the inductor, the equation is given by I equals to I naught sine omega t. Okay, we know it starts from 0 and then increase slowly according to the source. Okay, according to the values given in the source. It will increase, just that it's a bit slow. So when the AC passes through the inductor, the back EMF causes by the self-induction is produced by EMF B equals to negative L di over dt. From this equation, okay, we then plug into the equations and we obtain negative L di over dt I naught sine omega t. So EMF, which is also our VL, is equals to negative L I naught omega cos omega t. Okay. So at any instant, the supply voltage equals to the back EMF in the inductor, but the back EMF always opposes the directions of the supply voltage, which is representing by this negative sign. Okay, so if you want to write it as VL, then you just remove the negative sign. Okay, because what we want is just the magnitude. Okay, kita nak magnitude saja, not the direction. So it always opposes the supply voltage by negative sign. So VL is equals to EMF. Okay, EMF B, your back EMF. So the magnitude, okay, we're looking at the magnitude, which is equals to Li naught omega cos omega t. So this part is actually our V naught, VL naught, okay, VL naught. So this equation, VL, can be also written as VL naught cos omega t. Okay, VL naught cos omega t. And once again, based on the things that I told you just now, cos omega t at the same time is equals to sine omega t plus pi over 2. Okay, plus pi over 2. Therefore, VL is also equals to VL naught sine omega t plus pi over 2. Once again, the reasons why we want it in terms of sine, that is because our current is in terms of sine. Okay, that is because our current is in terms of sine. So both of them, they should be in a sine function in order to calculate the phase difference between them. If you have one cos and one sine, then you cannot calculate the phase difference. So now from these two equations, okay, you can then sketch the graph. So your current now start from 0. So your red line start from 0, and according to a phasor diagram, now I is lying on the x component because it start from 0. Whereas your V is now start from the maximum value. Okay, your V is now start from maximum value. So now you have a 90 degree right here. Projection. Okay, kamu nampak dia project. Okay, dia project from 90 degree from 0 degree. Okay, project. So then you have your angular velocity that is flowing in the anti-clockwise direction. So straight away, according to the diagram, what can you get? You get the phase difference between them, which is pi over 2 radian. Okay, pi over 2 radian, according to the diagram right here. And if you look at V and I, now which one is at the front? Of course, it's V. V is in front of your I because now both they are rotating in the anti-clockwise direction. Therefore, based on this phasor diagram itself, I know that V leads I by pi over 2 radian based on the phasor diagram. Okay, based on the phasor diagram. But if you want to do it by calculation, then of course you can calculate it by using delta phi equals to now phi V minus 5I. You can use I minus V also can. Okay, you can also use I minus V. It's up to you actually. So I have omega t plus pi over 2 minus omega t. So it is equals to pi over 2. So V minus I give you a positive value. Therefore, V leads I by pi over 2. Okay, ada typo di sini. V leads I by pi over 2. When it comes to I, okay, obviously I lags behind. Okay, I lags behind. So V leads I by pi over 2 radian, but I lags behind V by pi over 2 radian. So again, it's up to you which one you want to use in your calculation. Okay, which one you want to use in your calculations. All right, now let us go to the impedance again. So once again, Z is equal to V naught over I naught. According to our derivation just now, V naught is equal to Li naught omega. So you plug it into the equation, cancel out the I, sorry. Okay, cancel out the I naught. You have omega L equals to XL. Okay, so now you have another equation. And once again, because omega equals to 2 pi f, therefore XL can be written as 2 pi f L. This equation shows you the relationship between XL and L. All right. So the inductive reactance is the opposition of an inductor. to the alternating current flowing through it, and it is defined as, okay, so basically same as the previous case. You have a VRMS over IRMS equals to V naught over I naught. And once again, here you can just use RMS and naught because you have just one component. If you have more than one component, then you need to put a VL RMS and VL naught, okay, VL peak value. All right. So basically, okay, basically, when it comes to here, what you can say is Z is equals to V naught over I naught equals to VRMS over IRMS equals to omega L equals to 2 pi FL equals to XL. Okay, so all these things can be used to calculate the impedance or the inductive reactance in a pure inductor circuit. Okay, in a pure inductor circuit. And according to these equations, okay, now you have the relationship. You have XL equals to 2 pi FL. So XL is directly proportional to F. Okay, it's directly proportional to F. So from the graph, XL against F, now you got a straight line that is start from 0 because they are directly proportional. So it is not proportional to L. Why? Because if you remember, L and C, they all depends on the component. As long as you are not changing the physical structure of the component, then inductance and capacitance, both of them, they are a constant value. That's why in this equation, your XL is proportional to F. It does not being affected by L. Okay, it does not being affected by inductance. Dia cuma affect oleh frequency. Why? Because XL is directly proportional frequency. And when it comes to this equation, 2 pi and L, they are all constant value. Okay, they are all constant value, provided if you are keeping the same component without changing its physical structure. Right? So once again, inductive reactance is a scalar quantity and the unit is ohm. Okay, all of them, they have the same unit as the impedance. Impedance ohm, resistance ohm, capacitive reactance ohm, inductive reactance also ohm. Okay, also ohm. So the relationship between reactance and the frequency can be shown by using the graph in figures here. All right. Okay, so let us go back to the 5 terms just now. Okay, so just now we have these 5 terms. Okay, so we just add one more things here, which is the unit. So the unit for these 4 things, okay, is in terms of ohm. The unit for capacitance is farad. F. The unit for inductance is Henry, which is H. Okay, so make sure you are clear. Alright, benda ini memang paling biasa keliru di antara pelajar. Okay, dari segi unit dia, dari segi dia punya nama, dari segi dia punya simbol. Memang paling senang confuse antara pelajar. Right? So basically, we're done with the fundamental circuit. Okay, so now let's take a 5 minutes break. We're going to continue again as a 12:30. Okay, when we continue, we'll look at the combination circuit. Okay, kita akan tengok combination circuit. So now let's take a short break. Okay, kita rehat sekejap. 12:30 kita sambung balik. Okay, so meanwhile, you go through these 3 fundamental circuit first. If you don't understand these 3 fundamental circuit, then you wouldn't be able to understand the combination circuit, especially when it comes to which one is leading, which one is lagging. Okay, so now let us continue and see how are we going to solve a combination circuit. Now first, before that, let us go through these three circuit quickly. Okay, because like I told you just now, the most important things is to know how to sketch the phasor diagram. So when it comes to pure resistor, according to our derivation just now, V and I, they are in phase. Okay, they are in phase. So when they are in phase, what does it mean? It means both of them, they are lying on the same line. Okay, so that is the phasor diagram for pure R. When it comes to pure C, okay, when it comes to pure C, we know that I leads V. Okay, so when it comes to R, V, R, and I, they are in phase. That is the things that we know. When it comes to pure C, what happens between C and what happens between the current and the voltage? So VC, okay, VC, it lags behind, okay, lags behind I. So meaning that now my VC is right here. Okay, so this is VC, this is VR. And when it comes to pure L, what I do know is that my VL leads I. Okay, it leads I by pi over 2 radian. Okay, so this one lags behind by pi over 2 radian. So meaning that when it comes to the phasor diagram for my pure L, that is the position of, that is the relationship of VL and I. So basically, okay, it doesn't mean that I have to always stick to this diagram right here. You have to see, you have to sketch it based on the equations given. If equations give you I in terms of cos, then your I should be starting from a 90 degree. Okay, and then you sketch the positions of V according to the relationship between V and I in the pure, okay, in the pure circuit. So this is just, I'm going to assume all of the three I, they are all starting from 0 degree. Okay, they are all starting from a sine function. That's why now my VC is at a negative 90 degree right here. Okay, dia tak semestinya mesti VC jatuh pada paksi X, untuk pure capacitor I mesti pada 90 degree. No, not necessary. Okay, not necessary. So you can actually rotate the phasor diagram based on the equations given. All right. So now, how are we going to do a combination circuit then? So consider an AC source of a RMS voltage, VRMS, is connected in series to an electrical component R, C, and L. Okay, you have a source based on the combination shown below. And then the RMS current passes through the electrical component, that is equals because they are in series. That's why if you will recall the table that I give you just now, for I have just I, not IRMS and I instantaneous, okay, without subscript R, C, and L. Because I passes through every component, they are equal because they are being connected in series. Okay, you have a series connection between all these components. Okay, now let's look at the phasor diagram. When you have an RC circuit, okay, how are you going to form the phasor diagram? Actually, it's very simple. Recall the things that you learned in pure circuit. Okay, if you look at the diagram on the right hand side, this is the phasor diagram for pure R. This is the phasor diagram for pure C. Now you have an RC circuit. Basically, you just take these two phasor diagram and then you stack them together. Okay, you stack them together, and eventually that is the diagrams that you're going to get. You see, now you have VR lying on the X component, and then you have VC. Okay, VC pointing downwards. Exactly same as what happened in a pure circuit. So if you have an RC circuit, then you just stack these two diagrams together. Okay, and then your I, okay, your I is lying on the X component as shown in the original diagram. That's why in my original diagram on the right hand side, I let all three I, they all start from axis. Okay, your I must be pointing towards the same direction in order for you to stack them together. If your I, they are pointing towards opposite direction, then you have to rotate it a bit before you stack them. Okay, just like a C. C tadi yang asal, we have I pointing upwards and VC lying on the X component. So I rotate it a bit until I obtain a diagram like this. Then I stack them together to get a new phasor diagram for RC circuit. Okay, to get a new phasor diagram for RC circuit. then of course something is missing right here, which is you need to show the directions of omega. Okay, omega. So omega is always pointing in the anti-clockwise direction. All right, when it comes to RL circuit, you see what happens right here. When I stack them together, I have VR still lying on the X component. And then what happened is that I have VL now pointing upwards. Okay, my VL is now pointing upwards. Okay, now I don't want this color. Let me change the color. Okay, this one. Okay, my VL is now pointing upwards. So this is my VL. All right, so ignore VS first. I will tell you what to do with VS after this. Okay, now we just sketch the fundamental shape for VL, VC, VR, and also I. So I is still on the X component. Why? Because my original diagram, my I, they are all lying on the X component. Now, of course, your omega is in the anti-clockwise direction. So when it comes to RCL circuit, basically you just stack all three of them together. Okay, you just stack all three of them together with your VL going upwards, and then your VC pointing downwards, and your VR lying on the X component. Okay, lying on the X component. Now, one thing, if you look at this diagram, you have something called VL minus VC. Okay, that is actually not quite right. Okay, that's actually not quite right because it depends on your VL and VC. All right, it depends on your VL and VC. If your VL is larger than VC, then yes, that is the case. Okay, this is for the case where your VL is larger than VC. If your VL is equals to VC, okay, if your VL is equals to VC, then the diagrams that you're going to get is your VL and VC, they have the same length. Okay, VC, they have the same length. This is your VR, this is your I, and it will give you a resultant vector, which is just a VR left in the diagram. Okay, this is when your VL is equals to VC. The diagram right here in the original table is by assuming VL is larger than VC. Okay, that's why when you sketch it, now, when it comes to sketching, you sketch the original diagram first, and then you sketch the one with the resultant vector, VL minus VC. All right? Don't draw all diagram, all vector in the same diagram. I think that is quite messy for me. Okay, and then if you have a case where VL is less than VC, now even though it is very rare case to have VL less than VC, but it could happen, then what are you going to do? Then your VL should be shorter. The vector should be shorter than VC. Okay, and this one is still your VR, and this is your I. So the resultant vector would now becomes VR here. This is your I, and this would be your VC minus VL. Okay, and of course, all of them, they are still going to rotate in the anti-clockwise direction. Okay, because they are looking at phasor. Okay, because you are looking at phasor. So I want you to write these two down. Okay, I want you to write it down first. These two diagrams. Just find some space in your books, maybe at the bottom. Okay, for you to record these two cases. So remember, when it comes to RCL circuit, not necessarily must be VL larger than VC. You have to read the question. Because in a past year question, okay, dalam soalan past year, it actually happens once where they give students VL equals to VC. And then they ask students to sketch phasor diagram. Okay, they ask students to calculate the resultant vector. Resultant is just VR because VC and VL, they cancel out. Okay, so you yourself have to know what happens when it comes to RCL circuit. All right, so I give you 2 minutes to write down the one on the right-hand side. Okay, yang merah punya dan hijau punya. You write it down first before we continue to complete this table. Okay, so now let's see how to calculate total voltage, which is the resultant voltage, and then the impedance and also the phase angle. Okay, so one thing that you have to know, resultant voltage, impedance, and phase angle, it all depends on the circuit. It depends on whether you have one component, two component, or more than one, and it can be determined from the Phasor diagram straight away. Okay, so you look at the Phasor diagram. How are you going to calculate resultant vector for V? Since you have one V line on the X component and one V line on the Y component. Very simple, right? It's just like you solve any other resultant vector question. So when it comes to this case, Vs, okay, Vs can be calculated by using square root. So Vr lying on the X component, so Vr squared plus Vc squared. So that is how you do it. Okay, that is how you do it. So how are we going to expand these equations furthermore until we obtain Z? So from here, we can then expand the equation. Because we have VR and VC already, right? So we can therefore expand it. Okay, expand a little bit. Comes IR square, IR, and then square. Here would be IXC square, and then equals to I, so you factorize it out, square root R square plus XC square, okay, plus XC square. So you can factorize it out, okay, you factorize it out. So that is how you calculate Vs, the method that can be used to calculate Vs. If you rearrange the equation, okay, if you rearrange the equation, so now you have Vs over I equals to R square plus XC square, and thus it is equals to Z. Okay, Z equals to Rx square plus XC square. So from equations of a total voltage, you can then transform it into an equations that we use to calculate the impedance, to calculate Z. And as you can see now, when you have combination circuit, Z is no longer equals to R and Z is no longer equals to XC. Z is equals to square root R square plus XC square. So from here, you can actually, okay, you can actually form another set of, well, I would say another set of Phasor diagram that based on Z. Okay, in which if you want to sketch a Phasor diagram based on the Z, then this is your R and this would be your XC without I anymore. Okay, remember why? Because I'm sketching the diagram based on this equation. So Z is somewhere in between them. All right, and this would be your phase angle. All right. So based on the original diagram, the Phasor diagram, okay, this is a more appropriate. This is what we call Phasor diagram, the diagram with V and I. Okay, but of course, some books, they give you the Phasor diagram in terms of impedance. Therefore, I also show you the equations, the Phasor diagram in terms of impedance, right? But the more appropriate one, it should be from V and I, okay, because we sketch this Phasor diagram based on the sinusoidal waveform. All right, so Z is equals to square root R square plus XC square. Okay, and Vs can be calculated most of the time. We calculate by using the first equation. And this equation is coming from Phasor diagram. That's why when you have Phasor diagram, okay, that's why I keep telling you guys Phasor diagram is the most important. So when you have Phasor diagram, you will know how to calculate VR, how to calculate Vs, how to calculate Z based on the diagrams given. And also the phase angle. So by looking at the Phasor diagram, I know my resultant voltage, my total voltage is somewhere in between VR and VC. So the phase angle between Vs and I can be calculated by using, well, sine, cos, or tangent. It's up to you which one you want to use, provided if you have VR and VC. Okay, and also Vs, of course. So once you have a value of VR, Vs, and Vc, then you can determine the phase angle easily based on the diagram. So for this table, I'm going to derive it based on R and C, okay, because that is our original information that we have in our Phasor diagram. So tangent phi is equals to Vc over VR. If you expand the equation, you can also calculate tangent phi by using IXC over IR, which is equals to XC over R. So it can be determined by using these two equations as well, okay, the phi. So you just rearrange it until you obtain phi equals to the angle. All right, so phase angle phi can be determined by using these three equations, provided if you have VR and VC. Right? So VS adalah additional punya total yang Anda kira daripada VR dan VC. So this table, I just shows you how to obtain VS, Z, and phi based on the VR, VC. Okay, VR, VC, and I. Saya tak tunjuk kamu equations yang gunakan VS. And of course, if you already have the information about VS, you can use it. Okay, you can also use it to calculate impedance. You can also use it to calculate phase angle. Cuma di sini saya tunjuk Anda buat equation berdasarkan phase angle yang asas, phase angle yang vector phasor diagram yang asas, phasor diagram yang asal. Okay, yang sebelum kita mengetahui nilai VS. Right? So let's look at the second one. The second one, basically you just repeat the same thing, okay, but now you have VL pointing upwards, okay, and VR right here. So VS is still equals to VR squared, but now the one on your y-axis is just VL. Okay, so if you expand the equation, you have IR squared plus IXL squared. Okay, and then you factorize the I out, you got I square root R squared plus XL squared. Rearrange equations once again, you have VS over I, which is then equals to R squared plus XL squared. Okay, and then VS over I, which is equals to your Z. Okay, the total divided by I, that gives you Z. Z is equals to R squared plus XL squared, and then square root it. Okay, so that is the equations that you use to calculate total voltage and also the impedance when it comes to RL circuit. Okay, RL series circuit. Then the angles, again, just repeat the same thing. Okay, now I have tangent phi, which is equals to VL over VR. Okay, which is also not theta, my bad. It should be phi. Okay, phase angle. So which is equals to IXL over IR. Okay, and then it is equals to XL over R. Okay, so the phasor diagram. How about the phasor diagram? Now you have VL pointing upwards, right? Therefore, here you should have XL going upwards, and this would be your R. Okay, the resultant would be somewhere here, and the phase angle is between your Z and R. So that is the phasor diagram for the second one. Okay, for the second one. And the RCL circuit, it depends on whether you have a VL minus VC, VC minus VL, or whether they are equal to 0. Right? The diagram, okay, for the diagram itself. But when it comes to calculation, it's still the same. So VS is equals to, now what happened is that along X component, you have just VR, so you can write VR squared. But for vertical component, you need to calculate the resultant Y component. Okay, you need to calculate resultant Y component. So either VL minus VC or VC minus VL, but it doesn't matter. Why? Because you have a square right here. So after you square it, okay, it will just become a positive value. All right, so when it comes to writing it down the equation, it doesn't matter whether you use VL minus VC or VC minus VL. After you square it, you will get the same value. So it is equals to square root IR squared plus IXL minus IXC squared. So it is equals to I, and then R squared plus XL minus XC squared. Okay, rearrange the equations. You're going to get the same thing again. VS over I, it is equals to square root R squared plus XL minus XC squared. So Z is equals to square root R squared plus XL minus XC squared. So you derive all this equation based on Phasor diagram. That's why I keep telling you guys, when you have Phasor diagram, actually you can solve all questions in chapter 6. Okay, because quite a lot of things you need to calculate it based on a Phasor diagram. Always sketch the Phasor diagram even if the question didn't ask you to sketch. So when it comes to angle, again, just the same thing. Tangent phi equals to y component. Y component, now we have VL minus VC over VR. Okay, so if you expand the equation, you have IXL minus IXC over IR. Therefore, tangent phi is also equals to XL minus XC over R. When it comes to the equation, the Phasor diagram for impedance, this will be your R, this will be your XL, and this will be your XC. Okay, so the resultant is somewhere here. So let's say XL minus XC. Okay, that is the resultant. Okay, and then the Z. Okay, now Z, the positions of Z, it depends on which one is larger. Okay, if your XC, if your VL is larger than VC, then yes, the diagram right here is correct. Your VS is in the first quadrant. But when it comes to right here, you have VL less than VC, then your Z will be in the fourth quadrant. Okay, your VS will be in the fourth quadrant. So that is the difference. Okay, that's why I told you you have to be careful with the values of VL and VC. VL dan VC yang tak sama, dia bagi anda di VS dalam quadrant yang berlainan. If VL larger than VC, VS is in the first quadrant. If VL is less than VC, then your VS is in the fourth quadrant. If your VL is equals to VC, then VS is lying on the X component in the same direction as your VS, because when it comes to this situation, VS is equals to VR. Okay, so VS is lying on the same component as your VR, because your VC and VL, they cancel out each other. Okay, they cancel out each other. All right, so that is your combination circuit. Okay, the combination circuit. So I think I'm going to stop right here. Okay, we are done with all 6 circuit. And then, okay, after your holiday, we will continue with the resonance and also power. Okay, because that one will take another 1 hour. If I continue again today, I think well, it's too much. Okay, we'll finish at 1 p.m. So I'm going to stop right here. You just copy this table. You just write down all this additional information. Then you may leave the class. Okay, kamu catat semua yang ini, then Anda boleh keluar kelas.